Now, next unit 2 of fluid mechanics and hydraulic machinery is about flow through pipes. Topics that covered in presentation is about introduction of flows in through pipes, major laws in pipes, minor laws in pipes, derivation of Darcy Weisbach equation, problems on Darcy Weisbach equation. First, discussion about what is meant by flow through pipes. Flow through pipes. The fluid is flowing in a pipe under the pressure, under the acting of pressure. This case will be taken in chapter of flow through open channels. Here we will consider the flow of fluids through pipes under pressure only. Loss of energy of friction, loss of energy in pipes. When the fluid is flowing through a pipe, the fluid experiences some resistance, some backward resistance, that is called as friction, due to which some of energy lost there due to friction. Loss of energy is classified as energy losses, maybe major energy losses. This is due to friction and it is calculated by following formula. The formula in order to find out energy loss is Darcy Weisbach equation formula. Darcy Weisbach equation. Next, Cheggy's equation. Now in our syllabus maybe Darcy Weisbach equation in order to find out the frictions. Next, in order to find out the minor losses in pipes, there may be this is due to, generally minor loss is due to small losses only, sudden expansion of pipe. When there may be a sudden expansion, there may be a loss of water. Sudden contraction, whenever there may be a sudden contraction of pipe, there may be loss of energy. Next, bend in pipe. When there may be bend in pipe, there may be some of the loss of water is there. That is also one of the loss. Next should be fittings. Whenever pipe fittings are there, that means leakages. Leakage is also one of the cause. There may be loss of energy. That means mass of water entering, mass of water leaving is not equal. Whenever not equal, the minor losses are very small losses. But in case of major losses, major loss should be very high. That is nothing but a friction which is acting opposite to the direction of flow. This has been found by Darcy Weisbach equation. Next, when there may be any obstruction, like just like nuts and bolts inside the pipelines, otherwise any sedimentants like small stones or whenever they may be flowing, that also loss in minor losses. Next, Darcy Weisbach equation. This is an empirical equation in fluid mechanics named by Henry Darcy. The name is called as, the scientist name is called as Darcy, and other name is Julius Weisbach. Weisbach derived the expression for friction factor. Darcy Weisbach equation relates the loss of pressure, otherwise loss of head due to friction. Darcy equation relates loss of pressure or head loss due to friction along a given length of a pipe to the average velocity of a fluid flow for an incompressible flow. Darcy equation is generally used for in order to determine the friction factors, head loss due to friction along a given length of pipe, along the entire length of pipe, as well as average velocity of a fluid flowing in an incompressible fluid. The static pressure drops along the direction of flow. The static pressure P drops along whenever the fluid is flowing. There may be a drop of pressure. Pressure drop has been occurs in the direction of flow because stagnation pressure drops due to loss of energy to overcoming the friction as the flow occurs. There may be a loss of energy due to the friction. Next, in order to derive the expression for Darcy Weisbach equation, now consider a pipeline. Pipeline is moving with a discharge Q. Q is the discharge. D is the diameter of a pipe. Consider the pressure of fluid is flowing inside the pipe. Now, whenever the pressure is flowing inside the pipe, there may be a dry area. This is called as dry area, where the water has been flowing, and considering this is the dry area. Next, at a length of L, the dry area, the wetted area should be at a length of L. Now 1 and 2 sections, wet 1 and 2 sections, its pressure is P1 and this pressure is equals to P2. Now pressure P1 is acting towards and P2 is acting forward. by using of Pascal's law. Now the friction force, due to the friction force, the water has been flowing away from the flowing plate. Now this is the pressure force acting, the pressure of water is going in this direction, the friction force is acting in opposite in the direction. P1 is the intensity of pressure at section 1, P2 is the intensity of pressure at section 2. Now L is the length of a pipe, L is the length of pipe at section 1 and as well as section 2. Now D is the diameter, let D is the diameter of a pipe, F is the coefficient of friction, F should be the coefficient of friction of a pipe, type of flow, based on type of flow, depends upon type of flow, material of pipe, surface of pipe. HF is the head loss due to friction, where HF is the head loss due to friction in a pipe. HF is the coefficient, HF is the head loss due to friction. Pressure head loss due to friction. Using a Bernoulli's equation, we know the Bernoulli's equation, P1 by rho g plus V1 square by 2g plus Z1 is equals to P2 by rho g plus V1 square by 2g plus HF. Now we know the Bernoulli's equation from V1 by rho g plus V1 square by plus Z1 is equals to P2 by rho g plus V2 square by 2g plus HF. Sorry, it is V2 square by 2d. Now H1 and H for horizontal pipe, the head remains same. Whenever there may be horizontal pipe, Z1 and Z2 remain same, H1 and H2 remain same, then equation becomes P1 plus rho g plus V1 square by 2g plus P2 by rho g plus V2 square by 2g. Whenever uniform flow, I already discussed the uniform flow when the velocity remains same. Whenever V1 is equals to V2, the energy, now the equation becomes P1 by rho g plus V1 square by 2g plus Z1 is cancelled out, P2 by rho g plus V1 square by 2d plus H1, Z1 is 0 now. Now we get P1 minus P2 is equals to, by cancellation this one, we get this one should be cancelled out, this remains same. Whenever this remains same, P1 by rho g is equals to P2 by rho g is equals to HF. Now we can write as P1 minus P2 is equals to rho g HF. Consider it maybe equation 1. Now F dash is the frictional resistance acting per unit area along the vector surface. Along the vector surface per unit velocity. Frictional resistance F is equals to F dash multiplied with vector area multiplied with velocity square. F dash multiplied with vector area multiplied with velocity square. Now that is equals to F dash. The vector area is nothing but pi dl. That is circumference multiplied with L. Circumferential area multiplied with velocity is equals to V square. From that, frictional resistance F is equals to F dash. Now PD can be written as, pi d is nothing but perimeter. Perimeter can be written as P into L. Perimeter is P, L is L multiplied with V square. Now resolving the forces along the horizontal direction, we get P1 is P1A which is the pressure force. P1A is nothing but a pressure force which is acting positive direction. P2A which is acting in opposite in the direction, minus frictional force is equals to 0. Now from this we can ask P1 minus A, P2A is equals to F. Now P1 minus P2 into A is equals to F. We get P1 minus P2 is equals to F divided by A. Now substitute the values F and P1 P2 we get. We know that from equation 1 in the previous slide, equation 1, rho g HF is equals to P1 minus P2 is equals to rho g HF is equals to F dash P, F is F is this one, F dash PL V square divided by area. Now rearranging the terms, we get HF is equals to 4FL V square divided by 2G. P by A is called as vector surface area divided by area. Vector perimeter divided by area. Pi d divided by pi by 4 d square. We get by cancellation. P by A is equals to vector perimeter divided by area. We get 4 by d. Now by substitution, we get HF is equals to F dash rho g by 4L V square by rho g d. Substitute by Moody's chart by design, F by rho is equals to F by 2 we get. HF is equals to 4F LV square by 2GT. Get HF is equals to 4F LV square by 2GT. Now it is calculated. Now it is used to calculate the loss of head due to friction in the pipe. This equation is known as Darcy's Weisbach equation. This equation is known as Darcy Weisbach equation. Next comes to problem. How to solve the problem of friction resistance. In a pipe of diameter 350 mm and a length of 75 meter, water is flowing at a velocity of 2.8 meter per second. Find the head loss due to friction during Darcy Weisbach formula. We know that HF is equals to 4F LV square by 2G. Given diameter of 5D is equals to 350 mm, that is equals to 0.35 meter. Length of pipe L is equals to 75 meter. Velocity of flow V is equals to 2.8 meter per second. Kinematic viscosity. Kinematic viscosity also given. It is 0.012 stokes. 0.1012 stoke means we know stoke is 10 power minus 4 meter square per second. Get in the first unit 10 power minus 4 meter square per second. Now head loss due to friction HF is equals to, using Darcy Weisbach equation, HF is equals to 4F LV square by 2GT. Now Reynolds number, by using of Reynolds number, V into D divided by kinematic viscosity. V 2.8, D 0.35. The kinematic viscosity is 0.012 into 10 power minus 4. We get this value, Reynolds value. Now, when you want to find out the factor of friction factor coefficient, we have to find out the Reynolds number here. Now, in order to find out the Reynolds number, there may be a formula. There may be a remembering formula. There may be in design textbook itself, in heat transfer textbook itself. From data book, 0.071 is equals to Reynolds power of 0.25. And now the range is, Reynolds number is range is this one. Now friction, in order to find out the friction factor, this is a formula. 0.0791 divided by Reynolds number is this value. Substitute, we get friction factor. Now head loss due to friction. HF is equals to 4F LV square by 2GT. 4 F is 0.00263 75. F 4F L length is 75. D square V is 2.8 square. 4F LV square by 2GD. 2 G is 9.81. Diameter is 0.34. Now from that, head loss due to friction. From that we get as head loss due to friction is equals to 0.9 meter. Now the head loss due to friction is equals to 0.9 meter. This is the about Darcy Weisbach equation. Darcy Weisbach equation as well as the problem on Darcy Weisbach equation. It is the unit 2 of fluid mechanics and hydraulic system.